In this lecture, let us talk about bandwidth of angle modulated signal, where the message signal is an arbitrary signal. Okay, so we did the discussion with respect to very special modulating signal, that is your m of t is am times cos of omega mt. Now what we are saying is what is the bandwidth for an arbitrary signal. Okay, for this signal we said your x of t is equal to a times cos of omega ct plus beta times sin omega mt, right? That's what we said. And for this we found the bandwidth, that is 2 times delta f plus fm. So this all are for a sinusoidal modulating signal. Now let me take a general signal. M of t is a general signal. If it is a general signal, then what is the bandwidth of the angle modulated signal? Okay, so if you have done some discussion on feedback, so we are considering to start with the fm. So let me define your x of t is equal to a times cosine of omega ct plus 2 pi k suffix f integral of 0 to minus infinity to t, then m of tau d tau. This is my angle modulated signal. Now let me rewrite this. A times cos of omega ct plus kf m of tau d tau. Now let me denote this as a of t, just for a compact notation. So this is a times cosine of omega ct plus kf times a of t. Now the complex envelope of this signal is simply x tilde of t is equal to real part of e complex envelope, so therefore the carrier will not come. Let me put suffix xfm is e to the a times e to the j k suffix f a of t. Now this one is x suffix fm tilde of t, complex envelope. Okay, and this exponential function I can expand by using power series. Recall the power series. E to the x equal to 1 plus x by 1 factorial plus x square by 2 factorial and so on and so forth. 1 plus x by 1 factorial plus x squared by 2 factorial plus and so on and so forth. Therefore this I can expand in the power series. Therefore x tilde of fm of t is equal to real part of, let me take a outside. Okay, a is a constant, so I put a here. A times real of, expand this, 1 plus j times kf a of t divided by 1 factorial plus j square is minus 1 times kf squared a squared of t by 2 factorial. Plus j cube kf cube a cube of t by 3 factorial and so on so forth. Okay, close the braces. Fine. Now a times, you take the real part of this, so this is 1, real part of a is no, let it be as it is. Okay, so this is my x suffix fm of t. Okay, now this x of t, now this x of t I can write as x of t is equal to a times cos of omega ct. Let me rewrite one more time. Kf times a of t. This I can again write as a times real part of e to the j omega ct times plus kf a of t multiplied by j. Okay, now again a times real part of e to the j omega ct times e to the j times kf a of t. Okay, so what is e to the j times k suffix f times a of t? What is this? This one you expand in terms of power series. Just now we expanded, the power series is here. Okay, substitute for that, and that one will be x suffix fm tilde of t. Now you bring this guy a to the inside, real part of e to the j omega ct times a times e to the j k suffix f a of t, and this one we denoted by the symbol x tilde of t. Therefore real of e to the j omega ct, then x suffix m tilde of t. Real part of the x tilde of t is given here. Okay, therefore e to the j omega ct multiplied by 1 plus j kf a of t minus kf squared a squared of t by 2 factorial plus so on. Okay, you multiply, the constant a will come here. I did some mistake somewhere, the a is missing here. Okay, don't bring this a here. Okay, so leave this a here. So that's it. So let the a be here as it is, and let it be here as it is. Therefore the same A repeats here also, same A, so you put one more A here also, and this will not be there. Okay, so this is my x suffix f form of t. Now a times, right? Now you multiply inside and take the real part of that. So this becomes real part of a times e to the j omega ct plus j times a times k suffix f times a of t times e to the j omega ct minus a by 2 kf square a squared of t e to the j omega ct plus dot dot dot. Now take the real part of this. This becomes cos omega ct, and here this becomes that becomes a square j times j minus, because this becomes cos theta plus j sin theta, and that j sin theta is multiplied by j minus, that's why I put minus here, minus here there is 1 by 2. Okay, that's it. Because all other terms are imaginary terms, that's why. So let me write down the final result. Then this you replace by j times kf times a of t times cos omega ct plus j times sin omega ct, and this term also replaced by cos omega ct plus j times sin omega ct, and then finally write down the answer. Okay, so I am writing the final answer, final step. So in between the algebra you can do. So a cos omega ct minus a by 2 kf a of t sin omega ct minus a squared by 2 kf squared a squared of t cos omega ct, plus it keep on goes. Now let me say this is equation number 1. Okay, so this equation number 6 gives me, this is my x of t. So equation number 1 gives you a different way or a different look at the same signal, and this is the power series expansion. Instead of Fourier series expansion, you got a power series expansion here. Okay, so earlier also we obtained a series expansion, but there are major differences in these two series expansion. Okay, when you take m of t is a pure sinusoidal signal, then the expansion is in terms of Fourier series, and here it is in terms of power series. Okay, so there we used Fourier series, and here we are using power series expansion, because in the previous case we had e to the j times beta sin omega mt, and this is the periodic signal, so we used Fourier series. But this one is not periodic. Okay, this one is not periodic signal, so you cannot use Fourier series, because in this one a of t is arbitrary signal. Okay, this a square of t, a of t, these are all arbitrary signals. That's why we have taken the power series expansion. And equation 1, this also yields some very good insights. That is a very good understanding which we need to discuss a little bit. Now let us look at this equation 1 in some detail. Okay, in fact it is maybe let me make some space. I need a space for here, so let me delete it. Now if you look at very closely this equation number 1, it is clear that it is not a linear modulation at all, because you have terms like a of t, then a square of t and a cube of t. Therefore this is not a, maybe I'll write down here, not a linear modulation. Okay, it is a non-linear modulation. That is the first point we will observe. Okay, so but this becomes more explicit now. So what can you say about the bandwidth of such a FM signal? It has a pure carrier, a of t times a times cos omega ct carrier. Okay, and there is a component due to the modulation. This is the modulation, like a double sideband suppressed carrier, a of t times sin omega ct. Bandwidth of this will be plus or minus b around, because we know DSBSE how the spectrum looks like, right? Therefore the bandwidth is plus or minus b around the carrier. Let's say if this is carrier, then you have 2 fc plus b and fc minus b. The total bandwidth is 2b from the second term. Okay, term corresponding to a square of t has bandwidth of plus or minus 2 times b. Okay, around the carrier. As you can see, since this is an infinite series, therefore theoretically the bandwidth is infinity. So this is once again shows that theoretical bandwidth is equal to infinity. So spectrum contains various components. There is a component due to unmodulated carrier, that is the first term, that is nothing but carrier term. So the spectra of a of t and a square of t are translated translated around the carrier, that is translated to fc, to the upper sideband as well as to the lower sideband. So there are various components that you have here in this expression. One is carrier and the second one is spectra of a of t, a squared of t up to a to the n of t. Okay, translated by translated to fc. So this shows that it can have infinite bandwidth. For the narrowband FM, we know that we can approximate it by only first in that expression, and that's it. Okay, if it is narrowband, so no need to consider rest of the terms, only first sideband, first upper sideband and first lower sideband and carrier, that's it. Okay, now let us take a simple example. In this case, let us take instead of taking an arbitrary signal, let me consider a summation of two sinusoidal functions. Let's say k1 times cos of omega 1 t plus k2 times cos of omega 2t in the expression instead of m of t. Now if it was an AM signal or linear modulation, you will get components after modulation at omega plus or minus omega 1 and omega plus or minus omega 2. This is for AM case, but we are talking about FM. Therefore in the case of FM, not only you will have omega plus or minus omega 1, omega plus or minus omega 2, but also you will also have omega c plus or minus n omega 1 plus or minus n omega 2 in the frequency modulation. Okay, so this is the result that we need to remember. So it has omega c plus or minus omega 1, then omega c plus or minus omega 2, omega c plus or minus n omega 1 plus n omega 2. Now in this expression, look at the nth term in this expression. If you look at the nth term, then what will you have? Okay, remember when we discussed non-linear systems briefly, we discussed that it generates a digital frequency component. For example, if you consider the nth term, it will be a to the n of t, right? So this a to the n of t will produces not only n omega 1 and n omega 2, right? But it will also produces sum and differences with respect to the carrier frequency. Therefore omega plus or minus n omega 1 plus or minus n omega 2. Okay, where n and m are suitable integers. Okay, so in the FM case you have omega c plus or minus n omega 1 plus n omega 2, and these components are called intermodulation terms. This one is called intermodulation terms. Therefore FM generates, like any nonlinear system, intermodulation frequencies. But if you go back to the series expansion in this equation number 1, and say that the assumption say that the assumption kf times a of t is much less than 1, then once again we can approximate this equation 1 as series expansion by the first two terms, that is cos omega ct, and the second times a by 2 kf a of t times sin omega ct. When will you get these two terms? When a of t is less than 1. A of t times kf is much less than 1, then I can make the assumption that these first two terms have significant contribution than rest of the terms. This guy may not have significant contribution when this condition if you consider. Okay, so in that case you need to consider only the first two terms. So the assumption that we normally make for the narrowband FM is valid. So if as I said kf times a of t, you take modulus, okay, which is much less than 1, then the above expression reduces to fm of t reduces to a times cos omega ct minus kf a of t sin of omega ct. And now let me call this is equation 2, right? And this equation 2 will be somewhat similar with your amplitude modulation. Okay, the same expression can be valid for your phase modulated signal. Simply you replace this guy with the corresponding component. So I hope you get a different insight about the spectrum of FM signal. So this analysis does not help us to obtain a mathematical expression for the bandwidth because we have taken the arbitrary signal. So in that case we cannot get the closed form expression. But what is the objective? The objective was simply to appreciate better what will happen to the spectrum if the modulating signal is an arbitrary signal. I mean, what kind of spectral components you will see when the input signal contains more than one frequency components. Okay, more than one frequency component. So that was the objective of this discussion. So you not only get as I said omega c plus or minus omega 2, you also get omega c plus or minus n omega 1 plus or minus n omega 2. This is called intermodulation components, intermodulation terms. So that was the important point that we really wanted to appreciate. Therefore, if your modulating signal is a single frequency component, then you can express the frequency modulated signal by using Fourier series, okay, using your Bessel functions, and you can find the closed form expression for bandwidth of the FM signal. But if the input signal is an arbitrary signal, arbitrary message signal, then you cannot get that closed form expression. Okay, and moreover, if the input is an arbitrary signal, what does it mean? It has many components. Like if you take a speech signal, let's say starts from 50 hertz, 50 hertz, 51, 52, 53, like that. You have many more components, 50 hertz, 51 hertz, 52 hertz, like that. It goes up to, let's say, 4000 hertz. There are many frequency components. These all components will, add each other, and finally you'll get n times of omega 1 and n times of omega 2. Why did I put n here? Because n times I am multiplying your narrowband FM signal, because it is a nth square law device that I am going to use. So in that case, your carrier frequency and frequency deviation will be multiplied by n times of that frequency. Okay, so that's it about the generation of your FM that's it about the bandwidth of your FM signal for the arbitrary modulating signal. So let me stop at this point. Thank you very much.